Welcome to Lecture 9 of Submodular Functions Optimization and Applications to Machine Learning. And this is always the strangest part of the class when I'm beginning and I'm trying to figure out what to say. And I have no clue. Anyway, we have a reading assignment. And I've added a couple of additional assignments. And these are things that I'm hoping that you will just start looking into for yourself in terms of rather than it actually being a book that we sort of are obliged to purchase, like Fujishiki's book. These other sources here are very useful, and in some sense you could say that what we're talking about today is going to be drawing from all of them a little bit. Some of them are books like Shriver's 2003 amazing 3-part book on combinatorial optimization. Is something that everybody who's interested in combinatorial optimization and discrete optimization in machine learning should probably own. And I've also mentioned the Oxley book on Matroids, which is also a very good source, and a few other things as well. Weekly office hours are the same. Today what we're going to do is do something that I think some of you and perhaps all of you will find very interesting, but what we're going to do is we're going to morph from Matroids to polymatroids. And we've been talking about matroids, and we're going to see that polymatroids captures the essence. In a sense, everything interesting about a submodular function is captured in the underlying polymatroid component of the submodular function, as we've kind of seen. And you'll see that there's an analogous definition, and in some sense the way that polymatroids were originally conceived were sort of a continuous generalization of the independent sets of a matroid, which is not typically the way that you first see and you're first introduced to a polymatroid, but when you see it from this perspective, which is what we're going to do, you'll see how it really is just a very, very natural polyhedral generalization of a matroid. And I think it's kind of fun to see it this way. One thing I wanted to mention, so I don't actually have a slide on this, but there was a very nice question last time about the combinatorial geometries and hypergraphs. So I was thinking about that. So basically, however you define matroids as a set system, like for example, you can say you have a ground set and a set of independent sets. Or you could say you have a ground set and a set of circuits. Or you could have a ground set and a set of bases. Or you could have a ground set and a set of flats. I mean, in each one of these things, you could essentially give a ground set and a set of subsets which satisfy certain properties. In the case of it being an independent set property, you have the property that if you have a bigger one and a smaller one, you can take an element from the bigger one and add it to the smaller one. If you have a set of bases, then you can take two bases that are not the same and exchange two elements and still have bases. You have this exchangeability property. And there are similar properties. The one we didn't do in class was flats. So in each one of those cases, you can in some sense represent it with a hypergraph, right? Because you can basically on the left-hand side say you have your ground elements, and then on the right-hand side, you have your hyperedges, which correspond to, the members of the subsets. So what we were seeing last time was with regard to these specific forms of projective geometries, the goal there wasn't necessarily so much only to define the dependent sets, but was to sort of show in a sort of semi-pseudo-geometric fashion the dependence relationships in a way that sort of, resonates with our intuition of Euclidean geometry in R3. So like, for example, if you have 3 points and they're on a line, then we can say, okay, these things are affinely dependent, and so therefore they should be dependent within the matroid. They should only have rank 2. Or if you have n points on a line, then all of those n points have rank 2 because they are on the same line. And then we started saying, well, maybe regular R2 or R3, Euclidean space doesn't allow us to represent all matroids, so then we could start doing curves and everything. So the idea there isn't necessarily to sort of just identify subsets of sets, which in any of the definitions of matroids we could actually do with a hypergraph. Here it's really just to sort of allow us to still use some of our intuition in geometry and sort of to define things and to be able to easily see these sorts of things. Now one thing about hypergraphs also that's necessary, so in the geometries that we were seeing, it's necessary to designate whether or not a particular subset is a line or a plane or space or something else. Because let's say that you have a set of points all contained within the same line, then all of those points have together rank 2, and subsets of them have rank 1 or 2. So in a hypergraph, you would need to type the edges with, if you were to do something like that, you would need to type the edges with a rank to say that, you know, this hyperedge corresponds to a line, or this hyperedge corresponds to a plane. But I did do a little bit of looking in my Matroid books, Oxley, and I didn't find anyone doing that. Although there are Matroids that have been defined based on hypergraphs, but that's a different thing. Like, for example, we've defined Matroids on graphs, cycle Matroids, and basically all the independent sets correspond to sets of edges that don't have any cycles in the graph. And in a hypergraph, there's also notions of acyclic hypergraphs, or generalizations of graphs. And there's the notions of trees, hypertrees. And in fact, those of you who know about graphical models know about junction trees. And junction trees are essentially a hypertree, where each node in the junction tree is a hyperedge, and where you're guaranteed that it's a tree. So basically, if you construct a junction graph, if you will, if you're familiar with that terminology, or if you have a hypergraph, and then you have all subsets of the hyperedges that constitute acyclic edges, acyclic sets of edges, that's also a matroid. That's a different matroid. And that defines the independent sets of a matroid.
Yeah, I guess the connection is actually not as, so I also do a little bit of thinking, and like, hypergraphs are just like too general, right? You can use matroids to help you sort of understand hypergraphs, but using hypergraphs to understand matroids is actually not that useful. So
because, yes.
It's sort of like the algebraic structure that matroids put on it that it makes it useful. So,
I think, I mean, hypergraphs are sort of a universally useful thing to know about and to use. I mean, we can define the bipartite neighborhood graph, which is a submodular function via a hypergraph. We can define matroid rank functions via a hypergraph via the acyclic structure. We could, if we wanted to define, like in these matching cases, you could say all of those bipartite graphs are hypergraphs. You could, if you wanted to, have typed edges and use that. But I mean, in this particular case, it's really, that wouldn't really be getting at the essence of the geometry, where the geometry is like we're again trying to represent it in some non-Euclidean space. And geometry, the combinatorial geometry, is that it is still some geometry, and there's geometric rules about points and lines and planes and flags and all those things within and within such a space. You know, it's not, maybe it's a very strange space. But within such a space, I mean, there are metric spaces that are non-Euclidean, right? You can have non-Euclidean metrics, but there are which we reason about, and these are in some sense geometries. And so this is another instance of a geometry. And so Crapo, for example, was very adamant. I've never met him, but from reading his readings, he seemed to be very adamant about that matroids were best seen as these generalizations of geometries. And I think there's some, that's very interesting because we can reason about matroids. We can quickly, what we like is graphical visual display so that we can quickly reason about something. So I sort of am very sympathetic to that point of view. Okay, so that's that question. I think that was the question that was the answer I wished I gave in last lecture. Okay, so here's a review. So we saw matroids and the greedy algorithm. And right, so basically the critical theorem is this one, that the greedy algorithm, this should say algorithm 1 here. The set system is a matroid if and only if the greedy algorithm works, where working means that for every non-negative weight function, that algorithm leads to a maximum weight independent set. Okay. And we also defined Matroid Polyhedra. So the first thing was PR plus, which is based on a rank function of a matroid, which is an intersection of an exponential number of half spaces. And we saw that in 2D we have, it's the non-negative orthint, we have 3 half spaces. And it basically has to have one of these forms. These yellow regions or these purple dots here, have to correspond. And so those essentially become the matroidal polytopes for these different rank functions. And we also defined another polytope. It's necessarily a polytope because we're taking the convex hull of a bunch of incidence vectors of independent sets of the matroid, which gives us this. And we looked at, and so here we have this thing down here, which is a polyhedron. And we're not, you could say, oh, right away it's obviously a polytope, but we're just sort of not doing that yet. I mean, I agree that we could call that a polytope. But we're saying we've got this polyhedron defined in 9.11 and a polytope defined in 9.10. And what we showed last time was that the independent set polytope was a subset of the rank polyhedron. And that was a proof I'm not going to go through again, but it's there last time. The critical thing is that we've shown that subset relationship. Or equivalently, here's the independence polytope, which is a subset of the rank polyhedron. And what we want to show, and where we sort of stopped in the middle of last time, was to show that, in fact, these two things are identical. Okay. And the first thing we did, which was a really important theorem because it's going to generalize to general polymatroidal functions, the first thing is that when we want to construct the maximum weight independent set, and we know this thing, and that's the maximum weight independent set, that's the thing that is solved exactly by a greedy algorithm when M is a matroid, then what that says is that that can be represented, in fact, fairly trivially by basically the sum of weighted valuations. So the weights are lambdas and the valuations are the rank valuations on this chain of sets. So the notion of chain means that it's basically a sequence of subsets that successive pairs have this subset relationship with respect to each other. It's called a chain. And moreover, that the coefficients lambda I satisfy the following, that you can, in a sense, when you've got the weight vector, you construct the coefficients to sort of reconstruct W, where we're taking basically a weighted sum of the incidence vectors of the elements in the chain of sets. Okay. And the way we proved this, I mean, I'm not going to go through it again, but again, you sort of just construct it and it just happens. So basically, we say, oh, look, well, obviously we can represent this weight vector in this way here, and then we define the chain of sets. We order the elements in decreasing order according to the weight vector W, and we define the chain of sets according to this order. So UI is basically just the first I elements in the order, where the order is based on the decreasing order of W, where ties don't matter. If there are any ties, you just take an arbitrary, break the ties arbitrarily. And then you define the independent, define this base to be those for which the rank has increased. And that basically corresponds exactly to what the greedy algorithm is going to do. It's going to sort descending, and then you can each consider an item, and every time the rank increases, you include it until you get a base. That gives you the maximum independent set. It's a greedy algorithm. And then we just sort of switch. We say, well, okay, we can the weight of this thing, we can write it in this way, right? Because of the way that we've chosen that particular order. It's a difference of ranks, and the difference of ranks are going to be either 1 once we've chosen, when we've chosen the element, or 0 if we've not, right? And then we just rewrite it in this different fashion. We just organize the sum differently, and we've got the sum of weighted rank functions. Everything is non-negative. Okay, so now, any questions on that? Yep.
So is the size of the ground set equal to n?
The size of the ground set is equal to n, but the independent set is not necessarily equal to n. The independent set is equal to the number of times that the rank is increased by 1, right? Because the base is going to be equal to the rank of the matroid, which could potentially be much smaller than n.
So it is possible to design this whole thing with taking subsets U which are not equal to the number of elements, and still this is for general view, right? It's not for.
Well, all we're defining the chain. It's a chain of length n. Okay. Defining the chain of length n, and so basically, but we're defining the independent sets to be only the cases where the rank increases. So the chain is going to be equal to the length n. But the points at which the rank increases, the number of increments obviously is not necessarily going to be equal to n, because the base is of size less than n.
And we can have u's less than n also. We don't actually need the u's, the subsets u1, subset u2, subset u3. They don't actually need to be the number of sets need not equal to the number of need not equal to the size of the ground set. So
the number of sets is equal to the size of the ground set. We've defined it this way. Okay, we have n sets. Okay, n sets. This is by definition. This is the theorem states. We've got n of them. Okay. Now, if it's not necessarily the case that the number of sets, in fact, it's typically not the case, unless you have a trivial matroid, it's typically not the case that the u's for which the rank increases is going to be equal to n. If you have the free matroid where everything's independent, then yes, the rank's always going to increase for every element in the chain. But here we're defining I in equation 9.21 to only be those points where the rank increases. Okay? Okay, now moving on. We've got a linear programming primal problem, right? Here's a primal problem which corresponds to essentially what we're trying to do. We're trying to maximize this linear function subject to x being in the positive orthant, and you have this exponential number of constraints. And we can, through this mechanical process that I talked about last time, construct the dual. And what the dual does is, first of all, it says, okay, well, you've got a vector that's exponentially long, okay? It's a vector that has 2 to the n elements. And so for every constraint in the primal, you've got an element in the dual. And so what the dual function takes the form of the following. So we're minimizing over a sum that has an exponential number of terms of yu times the rank, subject to, again, positive orthant, and then this other constraint. And again, like I said, this is a mechanical process to get this dual. But I'll just say we've gone through that mechanical process, we've got the dual. Okay. And because it's a linear programming problem, we've got strong duality. So that this maximum subject to these constraints is equal to it has value equal to this minimum subject to these constraints. Strong duality. So that means we can sort of equate them with each other, okay, because we've got strong duality. Now let's consider again the linear programming primal problem. And note that this is essentially identical to this. It's basically maximizing this linear term such that x is a member of the rank polytope. Right? So that's a very sort of shorthand way of saying, well, it's a linear programming problem. It's got how many constraints? It's an exponential number of constraints. Now, normally when a linear programming problem has an exponential number of constraints, that makes the linear programming problem very hard. Right? It's linear in the number of constraints, the cost of the polynomial in the number of constraints. But if you have an exponential number of constraints, then the linear programming problem is hard, typically. And here we have indeed a polytope that's defined by the intersection of an exponential number of half spaces. Now, the other thing we have is that if we were to consider, we do have this inequality here, right? Or this set inequality where we've said that the convex hull of the characteristic vectors of the independence vectors of the matroid is no greater than the rank polytope, or polyhedron, sorry. And therefore, that if we consider this maximization problem, that's going to be no greater than this maximization problem, right? Just because we're increasing the set over which we're maximizing. Okay, so then we have the following set of inequalities. We've got a maximum weight independent set, which we said was solved exactly by the greedy algorithm. That's less than or equal to this. And why does that hold again? Because why? Why is that yellow thing true? Well, because the independent polytope is the convex hull of the incidence vectors of the independent elements of the matroid, right? Or independent sets of the matroid. And so therefore, the right-hand side includes all of the solutions to the left-hand side and more. So we're relaxing the constraints, right? So every w of I for all independent vectors corresponds to w times x, for x being the incidence vector of an independent set of a matroid. But we're also considering the continuous relaxation, so the only thing that can happen is that the inequality is of this way, where it potentially could get bigger. And then we've also said that the independent set is going to be a subset or equal to PR plus. So we've got that, right? And let's just define it to be alpha min, and this is the dual. So this comes from strong duality. So let me highlight the strong duality bit. So strong duality comes from this part here in green. Okay? Now look at the right-hand side form. It's the min over essentially a set of weighted combinations of rank valuations, right? And we've got an exponential number of rank valuations, exponential number of weights. We have to have non-negativity, and we have to satisfy this particular thing on the right. So this defines feasibility. It's non-negative, and it satisfies this inequality. It's a single exponentially long inequality. But wait a second. We already have something that's very similar to the right-hand side, the dual. Basically, what we showed in theorem 8.6.1 was that this maximization, the maximum weighted independent set, can be represented in this form. Right? Now look at the right-hand side of 9.9 and look at the right-hand side of 9.8, and you tell me, so is the right-hand side of 9.9 feasible for 9.8? Well, on the one hand, the lambdas are all non-negative, right? So we're cool there. And secondly, we have equality, that if we take the sum of the weighted incidence vectors of the sets that we're choosing, we've got equality with W. So basically everything is feasible, right? Everything on the right-hand side. So we've got now feasibility there. So therefore, we also have that since the right-hand side here is a min, this is equal to the min, we have that the maximum, which is equal to this, is going to be greater than or equal to alpha min, which is just by definition that thing. So we've got both equalities. So therefore, we've got on the left-hand side, we've got the max, all this stuff here. The max is less than or equal to this alpha min, and down below, we've got that this max weighted independent set is greater than or equal to alpha min, which basically means that all the inequalities have to be what happens to all the inequalities in equations 9.6 and 9.7? They become equalities, right? All the above are equalities, and so we can just turn them into equalities right here. So the bell agrees. So now what we've got here is that these two things are equality, and that's for any arbitrary direction vector W, right? Or any non-negative direction vector. And so therefore, it must mean that the independent polytope is equal to the rank polytope. Let's call it a polytope now, even though we knew it was a polytope before. So thanks to convex duality, we've shown that these two things are identical. And the theorem we've then proven is that this is true. Any questions on that? And moreover, that the greedy algorithm is fundamental for this, right? Because the greedy algorithm gives us actually a way of doing some really interesting things. So let's just summarize what we've done to make sure that it's clear. So for each independent set of a matroid, we can form the incidence vector, which is 1 of I, right? This is a summary now of what we've done. We can take the convex hull of the incidence vectors and we get the independent set polytope, which is Pn set. We can take the rank function of the matroid and construct the rank polyhedron. And the theorem says that they're identical. So we can describe the independence polytope of a matroid using the set of inequalities. And so basically, perhaps most interestingly, that this particular thing, like consider this linear programming problem. This is a linear programming problem highlighted in yellow that has an exponential number of constraints. That the valuation of this corresponds precisely to the maximum independent set problem that was solved exactly by the greedy algorithm. In fact, it's the defining property of the matroid. So therefore, that means that this linear programming problem, we don't need to run your favorite C++ optimized linear programming solver, you can just run the simple greedy algorithm and you'll get the solution. Exactly. In very, very low order polynomial time. So sometimes the greedy algorithm can be used to solve things that are maybe not obviously matroids. Like, for example, in this case. So that seems like a useful thing, right? And in fact, it is. Any questions on that point? So if this was a Coursera course, we would pause now and pop to a different screen, and then there would be a different voice that very pleasantly asks you the following question. Must it be exponential time to solve a linear programming problem with an exponential number of constraints? A, yes. B, no. C, I'm not sure. D, perhaps. So what's the answer? Perhaps? And then if you give the wrong answer, then it'll pop you to a different screen that says, recall. 3.2 minutes ago when we showed the following property. So, but this is not a Coursera course, so I'm not going to do that. So, yeah.
I guess I have a question on kind of implementation. So a lot of these algorithms kind of assume that the rank function is just, or computing the rank is just kind of a one-off thing, like it's a black box, but it's not always trivial, I guess, to compute the rank, or like if the rank increases or is it? So do you have to factor that into
the computation?
To the
Absolutely. I mean, so if you're doing this for real, I mean, well, first of all, I mean, just even representing an exponential number of inequalities and setting up your linear programming problem is not going to be feasible, since you probably will run out of memory before you actually get a chance to even express the problem. But I mean, many rank queries are queryable, and when you're doing the greedy algorithm, you can get it essentially to query the rank function n log n times. So obviously, if your rank function query is costly, it's going to be n log n times the cost of querying the rank. But if oftentimes your rank is very fast. And actually, I mean, because you know the pattern of the rank, I mean, so you know that it's specifically a greedy algorithm, so that you know that each rank is always going to be a superset of the previous rank, right? Because you choose the rank that increases the most, and the next one is a superset, and the next one is, and you construct this chain. That for many, many matroids, if you sort of have a particular structure which is representing the matroid, you can be smart about the query, because you know that the next one is going to be superset. So you can sort of set up the data structures to sort of, you know, evaluate a chain all in one fell swoop, as opposed to sort of, you know, treating it entirely as an oracle query where each rank query is independent of the other. And that can give you enormous speedups. Like that can give you amortized order n time, so that effectively it's really order 1 per query. So that's, I mean, in practice, when you really want to do this, and this is, by the way, I should say, true of submodular functions as well. I mean, for when you have a submodular function, and you're going to see that we're going to be using the same kind of greedy algorithm on submodular functions. In fact, we're working on that right now. So Rishabh is working on building up a fast C++ library of submodular optimization, which includes tricks like that. So, okay, so what if we consider the convex hull of incidence vectors just corresponding to the bases rather than all independent sets of a matroid? So if we define a polytope that is defined by the following constraints, so it's exactly the same, where it's the non-negative orthant, it has to be rank constrained, but at V it has to be equal to it. Okay. So this requirement is different, right? It's the third requirement. It's basically saying that x of v, that the sum over all elements in the vector. Remember, what does this equal? Just to make sure this is super clear, this really equals the sum for v in v of x of v. It's just the sum. It's the component sum of the vector. It has to be that one value. So you're only considering that one hyperplane. That turns out to be the incidence vectors of the bases. So it turns out that this polytope and the polytope corresponding to the convex hull of the incidence vectors of the bases turns out to be identical. And you can use the same properties. And I'm going to leave that as an exercise for you to do for your homework, because I think it's worthwhile going through. Does anyone have any idea what it looks like? So if we define some axes down there, and so let's use this particular matroid, like this one. So then what it would look like would be just this pink part. Right? So it would just be that face. This is the base polytope. Oops. So the base polytope is something that we're also going to see when we define polymatroids, and that has a particularly useful thing. But here we're seeing it just in the context of matroids. Okay, so there are other polytopes that we can define. There's something called the spanning set polytope. So remember, what does it mean to span? So if you're a set and you're spanning in a matroid, it means that your rank is the same as the rank of the matroid. Right? And we have this nice relationship with respect to this. We can actually define any spanning set. Like if it's a graphic matroid, it would be a spanning tree, or anything that's superset of a spanning tree. So anything that contains a spanning tree, or anything that contains a spanning set, a minimal spanning set, is or anything that contains a base is a spanning set. So you could take the incidence vectors of these spanning sets and take the convex hull of those incidence vectors, and then that would define a polytope. And the spanning set polytope. So in some sense, like all of this stuff, when you take the convex hull of the independence vectors, it's kind of like each element is, even if it's not one of the vertices of the polytope, it's kind of like independent in some sense, because you're combining independence vectors. Here what you're doing is each element of this polytope is kind of like a dependent vector, because you're taking convex hull of all of the dependent vectors that are spanning and are dependent. Or not necessarily dependent, but it's spanning. So everything sort of has got everything, or possibly redundancy in it. And so the spanning set polytope is actually determined by the following equations. First of all, it lives within the 0, 1 hypercube, which was what that first thing says. And then secondly, it has to satisfy this inequality. So it's a lower bound. So what might this look like? I mean, let's look at it in the case of the 2D matroid. So it's basically this little green region here. So remember, it's sort of like the complement, not surprisingly enough. Remember before we said that the independence polytope was this pink region, and now the spanning polytope is this green region. Okay. So how do we prove then that this is this bit is the right expression? So we do that by recalling our friendly neighborhood dual matroid, which basically says that you're independent in the dual if you're spanning in the primal, or you're independent in the primal if you're spanning in the dual, and that's what we're using here. So you're independent in the primal, you're spanning in the primal if you're independent in the dual, if the complement is independent in the dual. I forgot about the complement. I should have said complement. So you're independent in the dual if your complement is dependent, is spanning in the primal, or vice versa. I'm sure one of those ways was right. Just don't listen to me, just read the slide. No, that's not true. You're spanning in the primal if your complement is independent in the dual. And so we have, what we're going to show is that if you're an X and you're in this spanning polytope, then 1 minus X is going to be in the independent polytope of the dual, interestingly enough. Which, sort of like the complement, the relaxation of complement in the hypercube is 1 minus that guy. So it's like a hypercube complement. So how do we do this? So how do we show this property? Well, first of all, note that if you're in the spanning polytope of M, then that basically means that you're a convex combination of a bunch of spanning of the characteristic vectors of a bunch of spanning sets, right? That's just by definition. Because the spanning polytope is the convex combination of all spanning incidence vectors of all spanning sets. Now, if we were to take 1 minus x, so let's take some x, which is in the spanning polytope. So 1 minus x, this is the vector of all 1s. We can also say it's the incidence vector of E, of the ground set. And so then we can write this way. But because basically the incidence vector of E is equal to this convex combination of 1s, because essentially the convex coefficients sum to 1, we can write 1 minus x in this fashion. It's like a convex combination of complements of the spanning sets in the primal, which turn out to be independent in the dual. And so basically here what we're doing is we have this convex combination of independent sets in the dual, which basically means that 1 minus x lives within the independent set polytope of the dual. Right? So using that fact, so I mean we do have this is true, so it's non-negative orthant, right? Because x is in the hypercube. And then we can write it in this fashion. So 1a, so independent in the independent set of the dual, it basically means that 1 minus x, which is equal to the size of a, or 1 of a times x of a, which is the size of a minus x of a, has to be less than or equal to the dual rank function of a for all subsets of E. Because that's the definition, because we can use the independence set polytope or the rank polytope, because we know that those are equivalent now, right? And so then if we equate two things, we say, okay, well, we take this is less than or equal to that, but then we have the dual matroid rank function, which we proved last time or something. We cancel stuff out, and what we end up getting is the equality that we want. The inequality that we want. Okay. Any questions? So that's just a nice little other polytope. And there are actually quite a large number of other polytopes and polyhedra associated with matroids, which we're not really talking about yet. But I do want to sort of give you a sense of where we're going. So we've been talking a lot about matroids. And we know that matroid rank functions are a special case, and a very interesting special case of submodular functions. And what we're going to be doing is we're going to be slowly morphing from matroid rank functions to submodular functions. And we're going to be sort of jumping back and forth a little bit, but maybe a little bit more talking about polymatroid functions, a little bit less about matroid rank functions. And before you know it, you're going to be an expert in polymatroid functions. But armed with these matroidal toolkit, your intuition, and if it's not already, will be deep about submodularity. Okay, so everybody ready? So we're going to begin the morphing process. Everyone have their morphing hats on? I don't see anyone with a hat on in this room. There's someone way back in row 473, I think, but I can't really tell. So you guys can laugh louder if you want. No. Oh, that's good. Okay, so maximal. Let's just define the notion of maximality. So maximal points in a set. So S is a set. Let's see. S is a set, right? And X is a subset. And let's say there's some property P, and that's LaTeX mathfrax rendition of the letter P, which looks more like a B, but it's really a P. So you have some property, and you basically what the definition of maximal subset of a particular set S that has the property is A, it has to be a subset, right? So it's a subset. But on the other hand, it has to be something such that if you take any superset, it no longer possesses, it's either no longer a subset or it no longer has that property P. Right? So what we can say is that for all, for all v not in X, either X plus V is not a subset of S, or this property P, whatever, which looks like a B, is equal to false. Right? Okay, everybody got it? Maximal? So let's now talk about that in the context of a compact set in compact subset of Re. So what we mean by compact, so we're going to use this word relatively loosely. We don't need to use all of the measures theoretic precision that goes along with what's typically referred to as compact. So by compact, we're just, for all intents and purposes, just think of it as closed and bounded. So the sets we're talking about, the subsets we're talking about, are closed bounded sets. And that's what we mean by compact in our current context. So any compact set, we can say that a vector itself is also maximal with property P, or namely membership P, because anything with a property can be listed as a set of those things that have that property. So any particular P, which is a compact set, could be seen as the property set. And a vector X is maximal if it's the case that if you even move epsilon in the positive direction in any direction, you're no longer a member of P. So that's what basically this says. So this is maximal in P. And so here's some examples of maximal sets. So this red guy is maximal, right, over here. This is this one element is maximal. This whole thing, this whole line, these are all maximal. But these guys are not maximal because we can keep increasing in the vertical direction. Right? Here, all these guys are maximal, right? Because every time you take any point on here, you can't go that direction, you can't go that direction. And for this ellipse, basically everything to the upper right is maximal, and then similarly in the star, all this stuff is maximal here. Yep.
What is set S in each of these?
Set S is the shape. It's set P. We're not talking about S here. We're talking about P. So in each of these cases, what we're showing is a P. It's R2 rather than RE, right? And each one of these are sets, and we're showing the maximal points.
So I just thought similar in the the exactly opposite edge is also moving in the same direction, right? So if you define the property as in being in a particular direction, if you define the property as all sets of edges but all points moving in a particular direction, then opposite edges of the octagon, the third figure, will be in the same scenario, right? So basically what I'm asking is...
I have no idea what you're asking. I'm sorry.
If you look at the third figure, the bottom...
So is it this one here? Let's zoom in on this one. Okay, so it's this is the figure. So that now I know which figure you're talking about, which is...
So the bottom two edges, the bottom left edges...
Okay, but we're only defining maximal points within P. So in each of these cases, so here's P, right? Now P can be either seen as a property, or it can be seen as a set of points having that property. You know, anytime you have a property, you just enumerate all the things that have that property and stick them in some set, all of which have that property. And here what we're doing is we're saying points in Rn have the property. And so basically, there we go, right? So there's anything in the polygon has property P. Now if we want to say what's maximal in the P, it's basically all of the ones along this red bit over here. Okay? This red stuff here, all of those guys and all those guys are all maximal, because basically if we move any bit, if we move either up or to the right, we've left P. Whereas if we're here, we can move up or to the right, and we haven't left P, so we're not maximal. So it has nothing to do with what's going down here. In fact, I could take another thing that has exactly the same shape on the upper right, but it includes all of this stuff over here, and this maximal points would be identical.
But what I didn't get is, why is it that not all of the edges comprise the part of the maximal set?
Because those edges, as I just said, like all of the yellow stuff I just drew, you could take a different P, and the maximal set would be the same. The reason why these other things don't matter is because the only thing that matters is whether you can move up or to the right. This is this definition here, right? epsilon greater than 0 for all directions. If we move even the slightest bit up or to the right, or in our dimensions, if we move in the positive direction along any dimension, we've left P. We're right at the boundary. It's maximal. Does that make sense? Say yes. So that, okay. Okay. Here are some instances of non-maximal regions. But the regions are meant to be the green ones and not including the circle. So basically everything here is not maximal because I can keep increasing. As soon as I get to the circle, I've suddenly become maximal. These are all non-maximal. This is obviously non-maximal because I can move to the right, and these are non-maximal here. Similarly, this is non-maximal. Okay. So everybody get the idea of maximal, non-maximal with property P?
Wouldn't the green one just be the complement of the maximal set?
So I say again?
Wouldn't it, like, if you were to outline all the edges that were in non-maximal regions, wouldn't it just be the complement of the maximal regions on the boundaries? Because you just have like a small subset, because it's necessarily
that is true. I'm not saying that it's giving everything that's non-maximal. I'm just saying here are some examples of non-maximal regions. But yes. I could take the rest. Anything that's not the red would be non-maximal. True.
Maximal, non-maximal region.
Right. That I couldn't. We didn't say the maximal, non-maximal region, but we could have said that if we wanted to. I just want to make sure that the distinction is when it's maximal, when it's non-maximal. So remember, let's harken back to the days when we were young and wild in lecture 5. Sorry. Oh, question. Yeah. This is just the definition. Just by definition. Okay, so we are defining maximal to be ones for which you cannot move in the positive direction along any dimension, which in 2D means up and right. In 3D it means upright and forward. In 4D it means upright, forward, or in the future. 5D, I don't know. Does that make sense? Okay. Lecture 5. So remember, this is from lecture 5. So I think, we know this. We know what an independent set is. We know what a dependent set is. We know what a base is, and we know what a base of a matroid is. So here we can talk about a base of U. So we can talk about a base of a matroid, which is the maximal independent set of the matroid. But then if we have any particular subset, the base of U is basically the maximum independent subset of a particular set U. U might not be independent. U could be any set, and we can find a base of U. And we know in a matroid that bases, whether the bases of the matroid or bases of a particular set, have the same rank. Right? Any question about that? Review. Now let's define a subvector. Does anyone see where we're going with this? A little bit? So we have a subset. Let's define the notion of a subvector. A subvector y is a subvector x if its component y is no greater than. Okay, so what we're going to do is we're going to use this notation, x less than or equal to y. That means that for each component y of e, each component e, y of e is no greater than x of e. So y is the subvector of x. So how would we draw it? Let's use R2. So if here's x, then all this stuff here is going to be subvectors. Everything to the left and down. So if this becomes x, whoops, it's a very strange way of drawing. This becomes x, and then y is in this green region. Okay. So now the notion of a p-basis, it sort of combines maximality with subvector. So we've got a compact set P, okay, and we define and we pick any x, and so what we're going to say is a subvector y of x is called a p-basis of x. So it's a p-basis of x if y is maximal in P. So first of all, it has to have two properties. It has to be a subvector of x, and it has to be maximal within P. So in some sense, you're kind of taking P, whatever that region is, P is some set, and we're taking the intersection of P with all of the vectors that are subvectors of x, and then taking the maximal one, or the maximum. Then that's not necessarily unique. We're taking all maximal ones. So there's a couple of other ways. I'm going to write this in a few different ways. So y being maximal means that there's no z greater than y that's, so that that's also a subvector, but also within P. So here's another way of saying it. In still other words, y is a P basis of x if y is a subvector of x, and y is in P, the critical thing is and here, and y is in P, and anytime you nudge to the right or above or in the positive direction, you're no longer in P. So everybody get it? So it's very similar to like a base in a matroid, right? So in a base of a matroid, you can say, well, choose some set S. What's a base of S? Well, it has to be a subset of S, and it has to be maximally independent. Maximally independent subset of a set. Here, a P basis is a maximally independent subvector of a set. Sorry, maximally independent subvector of a vector. So it's exactly analogous, except that in the matroid case, we're talking about sets and independence. The property being independence that we need to preserve to be a base. Here we're talking about vectors and subvectors, and the property that we need to preserve is being a member of that set P. So P, that polytope, becomes analogous to the set of independent vectors in a matroid. Except that in this particular case, now we've got countably infinitely many of them. So here's the definition of a rank function. So the rank from the matroid is defined as the maximally independent subset of a set, right? That's the rank. Maximally independent subset of a set. And we can define the notion of a vector rank. So what's the rank of a vector? Now this is very different than the rank of a matrix or the rank of a set of columns. We're just talking about one vector. And what's the rank of that one vector? So first of all, we need to define it relative to a set P. So we've got a compact set P. And then we have this notion of vector rank relative to this P, which is defined in the following way. So we say, okay, the vector rank of x, where x is any arbitrary vector, is basically the maximum. It's a subvector, and it's a member of P. But over all subvectors and members of P, we take the maximal one, namely the one that has the maximum component sum. So it's like the maximum P-contained subvector. The rank is equal to the component sum of the maximum P-contained subvector of a vector x. Yep.
So can the vector rank be fraction, real number?
Can it be a real number? Yes. Very much so.
So unlike normal number.
It can be a real number. We're just summing the elements in the vector, right? Most certainly can be a real number. And now let's define B sub x as the set of all P bases of x. Namely, those are the vectors y that correspond to this solution. Now, we didn't say that these are, in 9.29, we didn't say that they're necessarily unique. There could be more than one, there could be one. But let's say that B script B of x is basically all of them. So all of the vectors such that when we take this guy, we get the rank. Okay? And actually, sorry, I said that not exactly right. So B of x is the set of p bases of x, right? So those are the maximal independent subvectors. Now amongst those, there could be one or more of them that have the greatest component sum. And so therefore, if we take the maximum over all of those that have the greatest component sum, and we sum them up and take the max, then we're going to get back the rank. Now it might be there's only one, like in this particular thing here, there might be only one p basis that has the greatest component sum, or there might be multiple of them that all have the same component sum. So that's what I meant to say. Now, the other thing that's worth noting is that if x is a member of P, then its rank is just equal to its component sum. Why? Because suddenly the P containing doesn't matter anymore. And so the only thing that matters is what's the maximal subvector of a vector? Is itself. So similarly, if you have an independent set in a matroid, what's the maximum independent subset of an independent set of a matroid? Is that independent set already? Right? Any subset is going to be independent, and itself is independent. So this is exactly analogous to like a self base. And so therefore we can call it a self p basis. Now the only thing that distinguishes one p basis from another is p. Right? P is the particular shape, is the particular subset of Rn, or Re in this case, that we're defining all of this stuff with respect to. Now, if we were to take any arbitrary shape P, like what if we take some crazy non-convex shape with curves and lines and wiggles and everything, all of these things may be either hard to compute or have ill-defined properties, or there might be no unique ones. Like for example, the notion of different p bases having different component sums is a very non-matroidal notion. Like if we wanted, for example, to sort of have this kind of property be such that we had the matroid property, which basically says that all bases of a set have the same cardinality, or if you take about the matroid, all bases of a matroid have the same cardinality. It would, if we wanted that to apply here, it wouldn't really make sense for all p bases to have different, or for different p bases to have different component sums, because component sum is kind of like the analogy to size in the set case, right? So we're going to now restrict ourselves to those sets P that have a property that is very analogous to the property that defines a matroid. Okay? And this is the definition of a polymatroid. And this is something that Jack Edmonds realized, and he did in the mid-1960s and published it in the late 1960s in his famous 1970 paper. And this was quite remarkable, and he was the one who did this. He single-handedly made this generalization. And he defined a polymatroid. And so what a polymatroid is, a compact set P satisfying its zero containing, so 0 is in the polymatroid. If x is in P and y is a subvector of x, then y is in P. So it has a down monotonicity property, or what we were calling a subclusive property. Right? I was trying to say subclusivity property, but I failed. So let's just call it down monotone. And then lastly, it has to be the case that if you take any vector x, then any maximal p-containing subvector of x, namely y, or any p basis of x, has to have the same component sum. So it's, again, exactly analogous to a matroid. So let's restate condition 3 in a couple of different ways. So that means that if you have any two distinct maximal vectors, y1 and y2 in P, they're both subvectors of x, and they're distinct, then they must have the same sum. Let's restate condition 3 yet again. For every vector in the non-negative orthant, every maximal independent subvector y of x has to have the same component sum, namely its rank. And so rank somehow suddenly makes sense. We can talk about the rank of a set, right? Because if it's the case that different p bases had different component sums, what would it make sense? Would it make sense to have a rank of a set? In a matroid, if it was the case that different maximally independent sets had different sizes, would it make sense to define a matroid? Sorry, would it make sense to define the rank? Because there's no sort of unique rank. It wouldn't make as much sense. So here's another way of restating condition 3. All p bases of x have the same component sum. So take which one you like. It's all the same thing. So this is a polymatroid. Now we've talked before about polymatroid functions. What we're defining here is not a polymatroid function. What we're defining here is a polyhedron, right? So, and it's actually, also pretty clearly a polytope. We haven't said anything about functions yet. Now, what we're going to see is that a polymatroid, in the same sense as a matroid rank and a matroid polytope defines a matroid, we're going to see that the polymatroid and a polymatroid function are the same thing, or at least they define the same thing. And then with that, we'll have that a submodular function is equal to a polymatroid plus a modular function. And so therefore, the polymatroid, this shape, this polytope sort of is the defining characteristic, or is a critical defining characteristic of any submodular function. But let's do a little bit more discussion. So vectors within P are called independent, right? Because analogous to the independent sets of a matroid, when you're in the set of independent sets, you're independent. And if you're outside, you're dependent. If you're inside of this polytope, then you're an independent vector. Now, this is for those of you coming, from hundreds of years of linear algebra background. It doesn't even make sense to talk about an individual vector that's independent. Nor does it make sense to talk about a vector and a single vector's rank. It's always in the context of other vectors, are vectors independent. Here we're saying that a single individual vector can be independent. And anything that's outside of P is called dependent. And then similarly, since it's a polymatroid, all P bases have the same component sum. Then if we take any P basis, y, then we can just sum it up, and that's going to be defined as the rank. So the rank is, in some sense, there's one reasonable value for P bases, and it's all the same. So therefore, we can just say that that's the rank. The rank of the polymatroid is equal to that. Okay, so let's do them side by side. So on the top we're going to see matroid, on the bottom we're going to see polymatroid. So a matroid is a set system, right? And a polymatroid is a compact set. A matroid is empty set containing, and a polymatroid is zero containing. A matroid is downclosed in the following way, that if we have any independent set and we take a subset of the independent set, that the subset's also going to be independent. A polymatroid is down monotone. So if we take any x inside of P and y, which is a subvector of x, then y is going to be in P as well. And then lastly, in a matroid, any maximally independent subset of a set A has the same matroid rank, which basically ends up being the size of the maximal independent set contained within A. And in a polymatroid, we're saying that any maximal vector y in P bounded by another vector x, or in other words, any maximally independent subvector of x, namely y, is going to have the same component sum, or the same vector rank. Any maximally independent subvector y is going to have the same vector rank. Okay. So the rank, in this particular case, the rank of x is going to be equal to the rank of y, right? So the rank of a vector is equal to the rank of the maximally independent subvector contained in P. So it's the rank of its P bases. Just in the same sense that the rank of a set x is equal to the rank of the maximally independent subset of that set X in a matroid. So do you see the analogy? Does everybody see the analogy? So let's do some examples. So this is a polymatroidal polyhedron, or a polymatroid. And the reason why they call it a polymatroid is because it's a polyhedron from a matroid. So one could call it a matro polytope or something. I don't know, but it's called a polymatroid. And so on the left-hand side, we've got P, and we have two possible x's. So first of all, like the subvectors of x are going to be all this stuff, right? And similarly, the subvectors of x are going to be all these things. And so the maximally independent P containing, namely independent subvectors of x, are going to be these ones on the left-hand side. And this single point on the right-hand side, this green point on the right-hand side. Now, for it to be a polymatroid, the polymatroid condition means that, let's take the left-hand side as an example. So all of the vectors corresponding to this green bit, let's just zoom in. So all the vectors corresponding to this green bit here have to have the same component sum. So what must that mean? So y1 plus y2, if y1 and y2 are the coordinates, basically all of those things have to sum to the same constant, which means that that line has to be, what does it say about that line? At negative, sorry?
Is it negative 1 slope?
Yeah, so it's can it be any slope?
No,
Negative 45 degrees, right? So the slope has to be negative 45 degrees. Right. So you can sort of write this, if you wanted to write an angle on it, as okay. Right, so we've already said that. On the right-hand side, there's only one point, so there's no constraint really on that one point. Right, so in this particular case here, it's just there's only one maximally independent P-containing, or maximally independent vector, and it has to have the same component sum as all of the other ones, but it doesn't matter. So here's some other examples. So when X is contained within P, again, X is its own P basis. So the constraint that it has to have, all of them have to have the same component sum, becomes vacuous. So it really only makes sense when there's more than one, or it only applies when there's more than one. But that's exactly the same in the matroid case. When you're already an independent set in a matroid, any maximally independent subset of that set is going to have the same, and there's one of them, which is itself, is going to have the same cardinality. It's only when you get something that's not independent can you potentially consider there being more than one maximally independent subset, which is the same exact thing that happens here. So again, the analogy is exact, except in this case it's a polytope. What about here? Are these polymatroids? Who says yes? And who says no? Okay. And some people didn't vote, so. But like all democracies, one has the right not to vote, and one can. So you've elected a non-polymatroidal president, but in this particular case, the majority was right. And the reason why this is not a polymatroid is because, all these guys here. Let's just use the left hand. Let's zoom in on the left-hand side, just in case this isn't clear. These are all the maximal independent subvectors of X. They're subvectors of X because they're in they're in this region, this whole region here. So, and then they're maximal because they're at the border of P. And if you move either to the right or up, you're no longer in P. But do they have the same component sum? No, they don't. So, because what is actually shown here is the positive orthant and a circle where each element squared has the same component sum, but not each element individual. So that doesn't define a polymatroid. And similarly here on the right-hand side, we don't have a polymatroid. It's the same shape. So basically it has to be the case that for all X, all maximal independent subvectors of a particular set have to have the same component sum. And so we have two different x's on the left and the right. So that doesn't change anything. Okay, let's play a game. Name that polytope, or sorry, name that polymatroid. So let's start with this one. Is this a polymatroid? The one on the left. What about this? Yes. What about this? No, it's not. Right? What about this one? It's a very thick non-smile. That's not either. So why is this one not? Because basically, you've got two slopes, right? So I mean, basically, you've got all of these maximal independent. Well, first of all, x is down at the bottom, but you can see right away it's not a polymatroid because of the two red lines. And you're going to have different component sums on each of those red lines, and those two red lines each correspond to the union of the maximal p-containing elements. This one is also not. What about this one?
Why are you even considering area outside X? We are only interested in subsets of X, right?
Well, let's consider them vertically. I mean, the point is the shape is either the polytope or not, and it has to be the case that for all x, all maximally independent subvectors of x have the same component sum. So when x is inside of the shape, it doesn't really apply. But when x is outside of the shape, like the lower part, it does apply, right? So let's consider them the corresponding vertical pairs, since it's the same example. So I should have shown you both of them. So we've got yes, yes, no, no. What about this one? This one with like a slide thing. No. What about this one here? Let's zoom in on this one. So like if we take this particular x, there's an independent guy, there's an independent guy, and all these guys are on the same negative 45-degree line. So is this a polymatroid? Yes or no? Who says yes? And who says no? And why not? If only that bell had come like 3 seconds earlier. Who said yes? And people raised their hand, and then the bell would have said, no, wrong answer. That would have been perfect. But the bell can't cooperate, can it? So why is it not a polymatroid? So for all x, all maximally independent subvectors have to have the same component sum. So yes, if you look at each one of these points, along here, they all have the same component sum, but basically it has to be relative to a particular x. So in this particular case, that's also a maximal independent subvector, and that's also a maximal independent subvector. So x has changed the set of maximal independent subvectors. Its p bases of x have to have the same component sum. And those guys are off this nice, beautiful 45-degree line, right? So therefore, this is not a polymatroid. So what is a polymatroid? It seems like we have three possible shapes. One case we saw before on the left, which reminds us very much of a matroidal polytope, right? Where we have as p bases all of these guys. Well, sorry, maximal independent sets. We have all these guys, right? As p bases of the polymatroid. Another one we saw, and by the way, so this sort of corresponds to what we saw in the Matroid case, that it has a rank of this one here. So this one on the left corresponds to where we have a rank of the rank of the Matroid is 1, and the number of elements is 2. And so there's sort of like perfect dependence. Like as soon as you have one element, then the other element is completely dependent. Is linearly independent. Is linearly dependent. This other case over here is also allowable as a polymatroid because there's only one p base. And so here here, sorry, let's go back to this case. So here, all of these p bases of the matroids are going to have the same component sum. And why is that? Because this green line is at negative 45 degree angle. Because we're taking the incidence vectors of the independence, characteristic vectors of the independent sets of the matroid. So that's going to have negative 45 degrees. Here, basically, we've got a matroid of rank 2 with 2 elements. And so there's only one p base of the matroid, which is the upper right point. And again, there, in that case, it doesn't matter. So that's also a polymatroid. So that seems to suggest, and then there was one other example we saw where we have just a single point there, where you have a matroid with 2 loops in it. Is that a polymatroid? Yes. So it seems like all matroid polytopes are polymatroids. But a polymatroid allows something more. It allows sort of this notion of partial dependence, and that's where this one comes in. So this basically says, so what are the, if we choose a particular x, say here, again, it doesn't matter. If we choose a point here, I think I've got some examples in a minute. But if we choose a point here, again, there's the maximal independent point, doesn't matter. Similarly, if I choose a point here, that's the maximal independent subvector, it doesn't matter. So the only thing that really matters is when I choose points out here, say. And so these become the subvectors, and all maximally independent guys, these p bases, have to have the same rank, and if it's at a negative 45 degree angle, then they're going to have the same component sum. So therefore, this, in 2 dimensions, this is sort of, in some sense, the most interesting shape of a polymatroid. So any question on this slide? Okay, so it's going to get a little bit trickier. So ask now or forever hold your peace. Is everything clear about what we've talked about? We'll see a lot more of these, by the way. So we'll gain a lot more intuition about polymatroids and polymatroid shapes in not just 2D but in 3D as well. So let's take a particular x. Okay, here's an x, and let's say that define S to be the support of x. So basically what the support function means is basically those are the elements for which x is non-zero. So we said x is in the non-negative orthant, so there's no negatives there, but it might have some zeros, and so the support are those where it's not zero. And so the complement of S, which is this, is going to be all of the elements that are zero. So if you sum all of the elements that are zero together, we're going to, of course, be zero. And so therefore, if we want any p base of x that has this property that that it's got some zeros in it, then the complement of the support of x in the p base is also going to be 0. So that
What's y here?
y is a p base. So like y is a, well, y, in this particular case, you can think of y as being any subvector of x in the non-negative orthant. So let's just be most general. This is for y less than or equal to x and y in p plus, sorry, r plus. Okay, so basically the zeros of x are going to force zeros of y. And so therefore, the only thing that matters when we're summing things up, so if we're constructing this component sum, if y was, say, a p basis of x, the component sum of E would only really mean that we need the component sum of y to be on the support of x, namely y of s. Okay? So it's really the non-zero elements of x corresponding to the elements of s, the support, that determine the component sum. Because since the zero elements don't add anything to the component sum. So what this means then is that if we take a particular vector x, right, And let's say that x is big enough so that for the parts of x, namely its support that are non-zero, let's say it's significantly outside of the polytope. Like, for example, in this particular case, in this figure, we've got an x whose support is y1, is dimension 1, right? Because in dimension 2, it's got value, that vector x's element is 0, right? So in some sense, then, when we construct the p-base of that, there's only going to be one possible element, which is going to be this guy. And therefore, what we can do is, if it's a polymatroid, we can sort of name the value of that element based on the support of x. And what if we were to, for example, name that value f of s? Right? So let me say this again, and this is not clear. So we take any x, right? We want to construct its p-base. But let's say that x isn't entirely all positive. So there's some elements. There's the support of x, which are the non-negative elements, which are the strictly positive elements of x, and the complement of the support, which are the zero elements. Now, for those elements that are in the support of x, let's say that they're big. So in this particular picture, we're saying it's 1 over epsilon times 1 over s. So where epsilon is small enough such that you're significantly far outside of the actual polytope. So that the thing that is actually defining the p-basis, the thing that is actually defining it is not x. It's not the subvectorness of x that's defining the p-basis. Rather, it's the polytope itself that's the p-basis, defining the p-basis. And since that value has to be unique because of the polymatroidal property, we can just name that value to be f of s, which is namely s is the support of that original vector. So what I'm getting at here is that we can begin to name these component sums based on a function of subsets of the ground set. And what we're going to be doing in doing this is moving from these ranks to the polymatroid function. The polymatroid function is going to be our rank function, which is only going to be a function of the support of the particular vectors, right? So that gives you a little bit of an intuition for the important theorem that we're going to prove, hopefully. Now, before we do that, let's just define a polymatroid. Let's define a polymatroid function. Okay. So, if only I had like 5-second warning for that bell. A polymatroid function, we know what that is, right? Basically, we're saying it's a normalized monotone non-decreasing submodular function. Right? We've seen this before. And we can also define a polyhedron associated with that submodular function. So very similar to what we did with respect to the rank polyhedron, we're going to define a polymatroidal polyhedron. And the polymatroidal polyhedron is defined by doing exactly the same thing as we did for the rank polyhedron, but rather than using the rank function, we're using the polymatroid function. Okay. Now this is something we even saw very early on. We said, oh, look at this polyhedron. But the critical thing, again, is that it's in the non-negative orthant, and it's defined as the intersection of a bunch of half spaces. There's an exponential number of them, but in this case it's a polymatroid function, so it's not necessarily a matroid rank function. So any of these polymatroid functions we know. Facility location, concave over modular, concave over non-negative modular, saturated graph cut, all of these things that we define in lecture 1 and 2.
I have a question.
Yeah.
What is significant of the first property in this context? Why do we need that?
Suppose it was the case that it was not normalized. Okay, so suppose like f of the empty set was -3. Okay, suppose I said this is a nice question. Suppose f of the empty set was equal to -3. Okay, so then my question to you is, would it be possible to define this polyhedron? So in this particular case here, I would get y of the empty set, and the only natural value for that y should be equal to 0, which has to be less than or equal to -3. So, and there's no vector that satisfies that property. So therefore, if it was the case that f of the empty set was negative, we could never define pf of plus.
Well, but what if it's because the positive value is non-zero?
Okay, well, I'm going to get there. But do you see this point? Okay, so if it's negative, suddenly 9.30 doesn't make sense. Okay. If it's positive, and if all the other things are still true, then basically what we're saying is that y of the empty set, which again has value 0, is less than, say, 3. So it's vacuous, right? Because all vectors satisfy that property. So either if it's the case that if you define that, if it's non-normalized, if it's negative and non-normalized, basically it makes it impossible to talk about this polyhedron. If it's positive and non-normalized, basically it's vacuous. And so let's just set it to be equal to 0 and just simplify. Since it doesn't add, it only either hurts us or adds nothing to do anything else. Does that make sense? Now, in general, what we're going to see, oftentimes we assume that the submodular function is normalized. And this often, in fact, if you read Fujishige's book, he says it like once, like in the middle of a sentence on page 3. And then for the rest of the book, it's assumed. So you're like on page 230, and you're reading some proof, and you say, why does this hold again? What? And then you have to go back to page 3 in the middle of that one sentence. So in Fujishige's book, he always assumes that the submodular functions are normalized, because it really doesn't add anything. You can always take a non-submodular function, subtract off f of the empty set, and you still get a submodular function. The minima are the same, the maxima are the same. It doesn't change anything. So let's look at the polyhedron associated with the polymatroid function. So let's do this in 3 dimensions. So we've got the non-negative orthant. Okay. We've got the 3 sort of axis parallel constraints. You've got these 3 sort of planar negative 45 degree constraints, and we've got this constraint here. So what might these things look like? Let's start off by using the asymmetric graph cut function. So this is a simple polymatroid function defined in this way. And here's the graph. So it's basically a graph with 3 vertices, v1 through v3, and 2 edges between v1 and v2 and v2 and v3. So you can actually reconstruct the standard graph cut this way. And so the polymatroid looks like this. And it's just basically 2 rotations of the same polymatroid. Polymatroidal polytope. So let me ask you this question now. So I've deliberately not named the axes. So what are the axes? It says the ground set is v1, v2, v3. It's a node function. So what are the axes? So one easy way of doing this is to just try some evaluations. So it basically has to be f of v2. What is f of v2 in this function? It's basically the number of edges. So v2 has got 2 edges, right? So that means that, and whereas f of v1 and f of v3 are both 1, so this is going to be v2 axis, and these don't matter. This is v1, and say this is v3. Right. Now notice that if you look at f of v1 and v2, or sorry, f of v1 and v3 is equal to 2, and so that basically corresponds to this plane here. Right? There's no constraint. It's full independence. Right? Because it's basically saying that x1 plus x3 has to be less than or equal to f of v1 comma v3, which is equal to 2. And so that constraint is non-active. On the other hand, if you look at f of v1, v2, and v3, that's equal to 2. Right? And so x1 plus x2 plus x3 has to be less than or equal to f of v1 It has to be less than or equal to 2. And so this whole plane here is part of the constraint. So like the sum, the component sum is 2 here. When V2 is 2, the component sum here is also 2, where only x2 is equal to 2 and x1 and x3 are equal to 0. And then here you've got x2 is equal to 1 and x3 is equal to 1, so the component sum is 2. And down here you've got x2 is equal to 1 and x1 is equal to 1, so the component sum is again 2. And so these are the 4 points of the active constraint. Okay, so we've done this. Here's another one. So I'm just sort of giving the valuation. So f of 0 is equal to 0, f of v1 is equal to 1.5, and so on and so forth. And here's the polytope associated with it. This is another polymatroid. Does anyone wish to guess the axes? Can you see the axes? Let me if I zoom in a little bit better. And now you can't see the actual equations. This is a lose-lose situation. How about this? I'll give you a hint. So this says 3 here, this says 2, and this says 1.5 right here. Maybe this is trivial. Is it trivial? What the names of the axes are? Sorry?
So let's say the vertical is V1.
Vertical is V1, yes.
And the bottom right is V3.
And the bottom right is going to be V3, yes. That's right, okay. Okay, so here's another one. It's just basically the modular, it's a concave over a modular function. So these are, by the way, these are the real polytopes. These are actually ones that were plotted based on MATLAB. So this is what they look like. So we're taking this particular modular function, and then we just define the square root over this modular function, and we get this. And I'm not going to bother naming the axes again. So again, you see certain things. So that each, it's sort of this, it has this sort of almost self-similar idea where, you know, you have these shapes. Each face sort of has the same kind of thing. But then you have this sort of constraining face. And then in higher dimensions, you get the same thing over and over again. You know, this is like, you could think of this as a projection down to 3 dimensions of possibly some higher dimensional polymatroidal polytope. Okay, so consider this function on integers. So g0 is equal to 0, g1 is equal to 3, g2 is equal to 4, and g3 is equal to 5.5. So this looks like it, you know, it's kind of like a diminishing returns-ish like thing. Is this function submodular? If you take g of this cardinality of S. No, it's not. It's not submodular, and you can see this in a number of different ways. If you take f of e1, e3 plus f of e1, e2, you get 8. But if you take f of e1, e2, e3 plus e1, that's going to be 8.5. Right? That's the union and the intersection. So therefore, we don't get the right inequality. Another way of seeing this, a very simple way, is just you can look at the violation of concavity. So if this was a concave function, we would have true diminishing returns. So g of 1 plus g of 2 minus g of 1 is equal to 1, right? Because 4 minus 3 is equal to 1. But g of 3 minus g of 2 is equal to 1.5. And it's a violation of what was required for a concave function. Because that increment, the increment of 1 in a concave function can only be diminishing, but here it's actually going up. Even though we've only defined, so this can't work.
Is that a necessary condition? So if you have a function over some modular function has to be concave in order for the composition to be submodular?
Mm-hmm. That's part of your homework, right? That was a long time ago, I know. We can still construct a polytope associated with this, but it's not a polymatroidal polytope. And the reason why is because maximal independent subvectors do not have the same component sum. So if we look at like this bit here, so every vector here in this little triangle guy has the same component sum, and those are maximal. But this point here is also maximal. And that, is maximal, but if we were to increase either in this direction or this direction, we would have to decrease in that direction. And that's not going to be on this 45-degree face here, which is this red thing that I'm filling in. So therefore, it's not a polymatroid. So to summarize, we have that a polymatroid, given a polymatroid function, we could define its polytope or polyhedron in this way. We have the definition of a polymatroid polytope, which is that it's a compact subset which is zero-containing down monotone, and for all x, any maximal independent subvector has to have the same component sum. Now, is there any relationship? Do you see the analogy between the Matroid case? So here we're basically defining this polymatroid polyhedron in 9.41, and we're defining essentially something that's analogous to the independent sets of a Matroid on the second bullet point. And it turns out that there's this very strong relationship between these two. And that relationship is that they're identical. Namely, that any PF plus, namely any polymatroidal polyhedron defined based on a polymatroid function, has the same component sum when f is really a polymatroid function, and that this satisfies the other properties. So therefore, it's a polymatroid. And here's this famous theorem. This is the famous theorem that will only begin, but let's just make sure that we understand it today, and then we'll prove it next time. But this is the theorem that actually has led. This is the thing that has led to it being possible to show that submodular function minimization can be done in polynomial time. And this was shown by Jack Edmonds again in the 1960s. So let's just read the theorem. So let's say you've got a polymatroid function defined on E, subsets of E, and you choose any vector from the non-negative orthant, and any PF basis Y. So remember, whenever we're talking about a basis, it has to be relative to some polytope in this particular case. And so the polytope we're using is the one that's defined based on the polymatroid function. And so we're saying that Y of x is a P basis, and we're putting a superscript x to sort of remind ourselves that this is really a P basis of x for that particular x. And it's also in the non-negative orthant. So then the question is, what's the component sum of Y? So for this thing to be a polymatroidal polytope, it must be the case that no matter what P basis we choose, the component sum has to be the same. Okay? So all P bases of x have to have the same component sum. So here's the component sum, right? Which is by definition the vector rank of x according to P. And the vector rank is equal to the max component sum. That's a subvector of x, and it's P containing, right? So then the theorem, that's all stuff that we know. The theorem is saying that that is equal to this. Namely, this submodular minimization problem. Okay. Now, one thing you should note right away is that if f is any polymatroid function and x is any vector, then we right away get general purpose submodular function minimization, right? Because yes, we're doing a and complement of a, but that doesn't really matter. We can always just put a inside of f and the complement of a inside of x, and that's just a constant. That's just a constant change, right? So therefore, this is really a general purpose submodular function minimization problem. But more importantly, we've actually shown a min-max relationship between what looks like a general purpose submodular function minimization problem, and something which looks very akin to finding the rank of a vector, which maybe we can find using something like the greedy algorithm, like we did in the Matroid case, or at least get some light onto it. But before we actually get to that, let's just talk about the sort of more the point at hand that we're trying to show us, which is that all component sums of all p bases have the same thing. Now, the reason why that's true is because the right-hand side, the thing I highlighted in green, doesn't depend on y, right? I mean, obviously, all p bases of x are going to depend on x, right? So the right-hand side depends on x. But there's nothing on the right-hand side that sums over that particular y. And it's saying for any p basis y of x, its component sum is equal to this green bit, which is this minimization problem. So therefore, all component sums of any p basis of a vector when it's a polymatroid is equal to the same value. And so therefore, it's a polymatroid, polymatroidal polytope. That's from this bit down there. So something else that's kind of interesting. Right, before we do that, let me just pause for questions. There must be some questions. If you want, you can sort of email me a question and I'll add it to the tape. Sorry, tape? What is tape? I don't know. I just showed my age. The spinning disc, whatever that is, those things. I saw them in a movie once. Black and white movie. Okay, so if there are no questions, then let's do this next point, which is the following. Let's say that we have a particular x and we take b to be the support of x. So b are the non-zero elements, and so the complement of b corresponds to elements all of which are 0. Okay? So for any element in the support of x, namely b, let's take that element is big enough. So the right-hand side, this right-hand side here, has a solution that's equal to the complement of b, namely a star, which is the solution of the min on the right-hand side of 9.42, is just equal to the complement of b. Now, why would that be the case? Because if the support of x is big enough, that min would never choose any a that contains any non-zero element of x. So therefore, it would have to be only the solution would have to, that solution f of a would just be based on the valuations of the polymatroid function. Okay. And so therefore, from the right-hand side and with the inappropriate x, you've essentially recovered the valuation. So the polytope has encoded within it all possible valuations of the polymatroid function. Namely, f of b is equal to the max of y of b subject to y being in this thing. And so that, I can kind of draw a picture. I think that might make it a little bit clearer. Do I have a space here? Let's add a little bit of a page. So basically, let's do some axes first. And then, so if you have this polytope, this polymatroid that looks like this. So obviously if we choose a point x, that's not what we mean, because we're not going to get anything. But if we choose a point like, say, here, we're going to get this valuation. Let's say that this is x1 and this is x2. Here we're going to get the value f of v1. Here we're going to get the value f of v2, where we're going to get if we choose this point. And if we choose both points, and notice, and if we can just choose that so that it's right on the origin of one of the axes, and so therefore it's just basically this valuation here, which is f of v1, or equivalently we can choose this point here, which is f of v2. if we choose it, say, here, we're going to get a p-basis there, which is going to be f of v1 and v2. So I've recovered all of the non-zero valuations of the polymatroid function from equation 9.43. Okay. Okay, so I guess the next thing to do is to prove the theorem. But if there are no if there are no questions, then are there any questions? If there are no questions, then we'll pause for now.